Welcome everybody, I am Alessandro Galeazzi from the University of Brescia and I will give you a presentation about our work entitled Reputation-Based Spectrum Data Fusion Against Falsification Attacks in Cognitive Networks. Over the past 20 years, the number of devices connected to the internet has been soaring and thus the connectivity demand has been increasing too. So, to increase the amount of communication opportunities in wireless systems, two main approaches have been proposed. Increase the bandwidth by adding new frequencies, and increase the spectrum usage by spectrum sharing packaging through cognitive radio networks. The key idea of spectrum sharing is that secondary users can opportunistically use frequencies reserved to other users, called primary users, if they are not transmitting. Clearly, secondary users must create minimum interferences to primary users and leave the channel as soon as primary users start transmitting. In this work, we consider a decentralized implementation of spectrum sharing. All the devices of the network can sense the spectrum to identify the presence of a transmission by primary user and report the decision to a fusion center responsible for the final decision on channel occupancy. This approach has some advantages. For example, it has better performances respect to a centralized approach when the system experiences deep fading or shadowing. However, it leaves room to some security threats, such as spectrum-sensitive data falsification attacks, where malicious users try to disrupt the system communication capabilities. We will show how it is possible to exploit spatial correlation among secondary users to secure the system against spectrum-sensitive data falsification attacks. In our analysis, we assume users are divided into locations and different location operates independently from each other, but the scenario is identical for each location. In each location, we have one primary user that is transmitting from time to time. We have secondary users that can sense the channel and report information to the fusion center. Secondary users also report reputation indexes, that is a number between 0 and 1 each user assigned to each other users. This index represents how a user considers reliable another one. We assume also that users can listen to the transmission of the spectrum information and reputation indexes generated by all other users. Moreover, users can be of two types, honest or malicious. Honest users aim at maximizing their communication opportunities and do not lie on sensing reports, but may modify reputation indexes to gain more communication resources. Malicious users lie on sensing reports and reputation indexes to disrupt the communication system. Finally, we have fusion center that asks and collects spectrum and reputation data generated by secondary users, and it generates channel occupancy, final decision, and allocated resources. We assume that it is also capable of splitting secondary users into locations. Thus, we focus on one location with n channels where primary user can transmit and k secondary users, and we define Gij as the reputation index given by I to j, and the global reputation index for user I as Gi. Gi is function of our reputation index a user gets from others. The key idea of this formula is that the global reputation index for user I is the weighted mean of the reputation indexes that other users gave to it, and the weights are the sums of the reputation indexes other users received. In this way, the judgment of users that received low reputation are taken less into account and weight less in the final decision on the trustfulness of user I. Theoretically, each user is requested to report a decision on occupancy for each of the channels, 1 if the channel is busy or 0 if the channel is idle. For each channel, the fusion center computes the weighted average of the occupancy report, using as weights the global reputation indexes of each user, and compare the result with a threshold tau that we fix as 0.5. If the function phi is greater or equal than tau, the channel is marked as busy, otherwise as free. In this way, Users with low reputation have less impact on the final spectrum sensing decision. Finally, Fusion Center assigns a percentage of communication resources to each user proportional to the global reputation index. The rationale behind this choice are from one end to discourage users' selfish behavior, and from the other, discard sensing reports of users with low reputation. We analyze the performance of the proposed mechanism by game theoretic paradigm. We first considered the case of only honest secondary users and the case of no sensing errors. We modeled the process as a repeated game, where secondary users periodically sense the spectrum, report results and reputation indexes to the Fusion Center, and listen to others' reports. The secondary user's set of action is the set of all vectors for reputation indexes, that is, a vector of k-1 numbers between 0 and 1. We assume that since secondary users want to increase their communication opportunities, they do not lie on spectrum sensing reports. The one-stage payoff is the percentage of resources they get at that stage. We also assume perfect information among users, and that users hold the same behavior belief. That is, they assign to a user the lower reputation index it gave in the previous stage of the game. Under this assumption, if we have more than 3 users, it is possible to prove that when all users assign reputation 1 to all others is an Nash equilibrium. We now introduce the presence of malicious users. We assume malicious users have a fixed behavior. They systematically report the opposite of what they sense, and they assign reputation 0 to every honest secondary user and 1 to every other malicious user. This assumption is intended to mimic a coordinated attack where multiple devices are controlled by a single malicious operator that aims at disrupting the communication system. Further, sensing error may happen when secondary users assess the presence of primary user transmissions. We consider 2 types of error. False alarm error, that is, when a user incorrectly marks a channel as busy, and we use false alarm probability PF to account for it, and undetection error, that is, when a user incorrectly marks as idle a channel used by primary user, and we use detection probability PD to account for it. We also have primary user transmission probability PTX that we fix at 0.5 since we assume we have no information about primary user. We can then compute the mismatch probability PM, that is, the probability that 2 honest secondary users have a mismatch in their sensing reports, as a function of detection and false alarm probabilities. If we consider n independent channels with identically distributed errors, the mismatch probability distribution is a binomial with mismatch probability and the number of channels as parameters. Notice that for symmetry reasons, this probability is also the probability of accordance between honest and malicious users. So, what happens when we introduce noise and malicious users? If honest secondary users adopt a naive strategy that reduces reputation as soon as sensing report differs, the system becomes dominated by malicious users, even if they are not the majority, as simulations show. This is because reputation among honest secondary users goes around 0 quite fast. To deal with noise and malicious users, we design a strategy that tolerates C-1 errors, that is, does not decrease reputation if there are less than C errors, but punishes users that do not follow this rule. For example, users that do not punish other users or users that alterate their reputation indexes to gain more resources. Notice that in case of person sensing, this rule leads to the Nash equilibrium where all honest secondary users give reputation 1 to each other. To test the performances of our system, we perform a simulation of the system considering 12 secondary users and 1000 rounds of sensing on 10 channels. And we choose the Fusion Center error rate, that is the rate of wrong channel occupancy decision, as evaluation metric. In this case, given the analysis of the mismatch probability, the maximum error a user tolerates is 5. As benchmark, we compare the performance of our mechanism with a simple majority rule. We start with 0 malicious users in the system. In this case, there are no substantial differences between the two systems, especially when false alarm probability is low and detection probability is high. When we introduce 3 malicious users, the impact on majority rule system is much higher than on reputation mechanism. Indeed, with the reputation mechanism, error rate is lower and the growth is slower when mismatch probability increases. This behavior is even more evident when we raise up the number of malicious users to 5. Here, the impact of malicious users on the majority rule system is stronger with respect to the reputation mechanism. As soon as mismatch probability increases, the error rate rises up quickly, while when reputation mechanism is employed, the error rate remains low until sensing reports are enough correlated. To conclude, we exploited spatial correlation that implies correlation on sensed channel status to secure a spectrum-sharing cognitive radio network distributed system. We use game theory to prove that secondary users are not incentivized to adopt selfish behavior, and we designed a strategy capable to defend the system against malicious secondary users. Simulations show that our mechanism performs significantly better than a simple majority rule, especially when the fraction of malicious users in the system is high and the sensing reports are enough correlated.